Our goal in this chapter is to investigate what's happening with what are known mathematically as series. Now, I don't think you can fully understand what's happening with a series until you fully understand what's going on with sequences. They're a little bit easier. So we're going to start there, and then once we fully understand what's happening with sequences, we'll expand on that knowledge into the concept of a series. So to define a sequence is a function whose domain is the set of positive integers. Okay, so we have a function which we should be very understanding of at this point, we should be very familiar with. The only difference is instead of allowing the function to have a domain of all real numbers, we have a restricted domain to just positive integers. Now, these positive integers, these are called the natural numbers. So the natural numbers. Whoops. Now, the natural numbers, they are defined, well, sometimes you'll see this notation, a capital N with two bars at one side representing the natural numbers. Ultimately, just know that when we talk about the natural numbers, we're talking about the numbers 1, 2, 3, 4, and so on to infinity. All right, not including 0, not including negatives, no fractions, decimals, nothing of that sort. So just whole numbers, not including 0. Okay. Now, what does that ultimately mean? Well, I mean, like I said, we've looked at functions already. We know a lot about functions. So for a function, if we have f of x equals, say, negative x squared plus 4, and it's defined on the interval from negative infinity to positive infinity. Well, we know that that function is going to have a graph which looks like a parabola, which is shifted up 4 units and pointing downward. Okay? Now, if we look at this in terms of a sequence instead, it's the exact same thing. Now, the difference is that when we look at it as a sequence, it's still a function. It's still the same definition of function. It's just only defined for x values that are part of the natural numbers. So instead of writing this set, 1, 2, 3, 4, ... we say x is an element of the natural numbers. So that just means x is restricted to only the natural numbers. So then the graph here would look a little bit different when we have, well, we can't have 0, so you can't plug in 0 because it's not one of the natural numbers. So you'd start with x equals 1, for instance, and then negative 1 squared would be negative 1 plus 4 would give us 3. So 1, 2, 3. All right, so there. And then when x is 2, that would be negative 2 squared plus 4, so that would be at 0. And then the next point on the parabola, and so forth. The scale's a little bit off here. It's going to run into my lower bound pretty quickly. But regardless, I think you can see what's happening. So we're just not considering any of the points in between here. We're only considering the points where we have values that are on integers. Okay? Now, you might be thinking, how does that change things? Well, we'll get there. We'll get there eventually. Let's just kind of understand what we can do with these to get started. Now, a few more definitions. So an infinite sequence is the ordered list of numbers that come from one of these functions. So a sub 1, a sub 2, a sub 3, and so forth. In our sequence, negative x squared plus 4, a sub 1 would have been 3. a sub 2 would have been 0. A sub 3, so this is where x is 3, so negative 9 plus 4, that would have been at negative 5, and so forth. And the nth term is negative n squared plus 4. We do tend to use n as the index variable here instead of x. X is generally defined as a real number from negative infinity to positive infinity. N, however, is sort of restricted for use with functions of this restricted domain to just the positive integers. Each number in that sequence is called a term, and we generally will use a notation instead of writing everything out. This is kind of like our function notation, a sub n. So a sub n would be the function itself. So in this case, it would be the function negative n squared plus 4. And then these values here tell us where that beginning and end of the variable n is. So it would begin at 1 and go to infinity. Now, for laziness, sometimes that's just left off, and it's sort of understood that it would generally run from 1 to infinity. So if you don't see it, just make that assumption. Now, the value n could start with 1, but that's not necessarily a general rule here. You can start it with anything that you want, including negative values and 0 if you want. It's just that it's more common to make the assumption that it's always going from 1 to infinity for simplicity, so that everybody's working on the same page. All right, so let's look at some examples here. So here's a sequence, a sub n equals 4n minus 2. All right, so a sub 1, a sub 2, a sub 3, a sub 4, and so forth. These values would all be known as the terms of the sequence. Now, it isn't particularly just a sub 1 is the term. You actually have to evaluate to a number. All right, so when n is equal to 1, we would have 4 times 1 minus 2. So 4 minus 2 would be positive 2. That's the first term of this sequence. When a is equal to 2, you just evaluate this function at 2. So 4 times 2 is 8. 8 minus 2 is 6. Then 4 times 3 minus 2, that would be 12 minus 2, which is 10. 4 times 4 minus 2, and so forth. This would be 14, it looks like. And we would eventually result in a sub n, and the nth term, of course, being 4n minus 2. Now, if we wanted to jump and say do like the 10th term, that's completely fine, because all we're doing is plugging in a specific value into this function, and that's no problem. We wouldn't have to do a sub 5, a sub 6, and so forth if we wanted to jump and do a sub 10. Now, another type of sequence is created through the use of what's known as a recursive definition. That wouldn't allow you to jump ahead. So what this means is each term in the list is defined based off of a function of the previous term. So let me walk you through an example here. So you have to have an initial value. All right, so we let a1 equal 1. Then a2 is defined as 2 times a sub n minus 1. So if we're looking for a sub 2, that's going to be 2 times a sub 1, because if n is 2, in minus 1 is 1. 2 times 1 gives me 2. So that's the second value in the sequence. The third value in the sequence would be 2 times the previous, so 2 times a sub 2, which would be 2 times 2 in this case because our previous value was 2. And that gives me 4. A sub 4 would be 2 times a sub 3, or 2 times 4 in this case, and that results in 8. Now, in a recursive sequence, we can't jump. So for instance, if I wanted to know what a sub 10 is at this point, or even just, a sub 6, the thing is, I would need to know what the previous one is, so 2 times a sub 9. But I don't know a sub 9 yet because I haven't calculated it. So I'd have to go back and do a sub 9, which would mean I need to do a sub 8, and so forth until I get back to a previous value. So you can't skip those values. Recursive definitions of sequences we probably won't run a lot into in this particular class, but it's good to just mention that they exist so that you know about them. They're somewhat common. You've probably heard of the Fibonacci sequence. So the Fibonacci sequence, whoops, I think I spelled that right with 2 N's there. Anyway, the Fibonacci sequence is a sequence of the form f sub n equals f sub n minus 2 plus f sub n minus 1. It depends on the 2 previous items and takes the sum of the 2 previous items. So you need 2 initial values. So like f sub 1 would be 1 for the basic Fibonacci sequence, and f sub 2 would be 1. So that you have the first 2 items in the sequence, and then f sub 3 is the sum of the previous 2. So 1 plus 1 is 2. And then f sub 4 is the sum of f sub 3, this one would be f sub, so f sub 3 minus f sub 2. So 3 minus f sub 2, or plus, sorry, would be 3. And then 5 and 8 and so forth. But again, you can't really jump values in between. You need to know the previous ones in order to calculate. Now, graphing sequences. We can do graphs of sequences, and that's generally one way of identifying what's happening to a sequence over a large period of time, because ultimately a graph is just plugging values into a function and plotting them so that you can see the relationship visually. When it comes to graphing a sequence, since we're only defined on the natural numbers, so the input values are just the natural numbers, which of course are 1, 2, 3, and so forth. So the input values are just these integer numbers here. All right, the output values, the y values, is just what you would get when you have a sequence. So this one's based off of 2 to the n, so a sub n equals 2 to the n. So this would be 2 to the first power, which is 2. So the y value here is 2. So 1, 2 is that plotted point. A sub 2, that would be 2 to the second power, which is 4. So you can see here this plotted value is at 2, 4. A sub 3, that's 2 to the third, which is 8, and so forth. So that's where we're getting these values at different points. So it's just a plot of the nth value and what that term actually evaluates to. So you can think of it as x and y pairs, of course. Now, of course, your calculator can do these. If you want to see what it looks like when you do a graph of a sequence on the calculator, you can do that if you go under the mode settings and just come down to where it says function and over to SEQ. That stands for sequence. So when you go into y equals, now you have some different options here. And to be honest, I don't use this often, but I believe what it allows you to do is define a recursive definition if you want, and you can plug that in. But I think we can just do, say, like, 2 raised to the n. And then we don't necessarily need to put in u sub 1 and u sub 2 unless we have a recursive definition. And then if you check the window settings, n starts with 1. That's good. That's where we always want to start with, unless told otherwise. N max is 10. That's fine. And then the plot start and plot step, just leave those unchanged. That's just going to, like the plot step, you could make it something different than 1, but we want all integers, so yeah, just leave those to 1. And then xmin, xmax, those are the same thing as in the what you would expect. So I'm going to change this y max, however, to, let's say, 20, and we should basically get the same graph. So there's what we have there. All right, now there's another tool here that I've created for you that you can use for both sequences and series when we get to them, and will allow you to do that. So let me pull this up and show you how it works. So this app is really more dedicated to looking at series, and it'll be extremely helpful when we get there. But you can do sequences. There's just not much that really happens with them. And another thing is that I've kind of set it up to where sequences don't show up quite as much as series, and that'll make sense later on. But basically you can put a sequence in. So for instance, if you have like 2 to the n, just type that in. So it has to be a function of n, so don't put in an x, it won't show anything. N start should always be at 1, and it doesn't allow you to change the n step because you always want to have integer based ones. So then hit update, and then that will graph it. And it just graphs the points. And if you'll notice, they show up very lightly because I don't want them to show up and be very prominent, which you'll see later. If you happen to be on a touchscreen device, you can actually change the scale pretty easily here and take a look at your sequence a little bit better, or you can use the X and Y zoom. So like for instance, if I want to see more of this scale, I can kind of, do this sort of thing. All right, but the thing is, this sequence is growing very rapidly. So no matter what I set my Y zoom to, like it's really gonna just run off to infinity very quickly. Okay, let me bring that back. Okay, and let's try a linear. So let's make it, I don't know, 3n plus 4. All right, now if I press update, you can see the linear relationship here. And linear functions don't run off to infinity quite as quickly, so if you'll notice, it does kind of make it all the way across the board on this particular scale that I have. But the you can see the linear relationship. There's not an actual line running through these points because we're only defined on the positive integers starting with 1. But you can see different sequences and what they ultimately look like in this applet pretty easily. If you want to compare it to another sequence, say like natural log n divided by n, you can do that. You can graph them both on the same set of axes. If you hit update, if it doesn't show, that means it either there was some sort of typographical error, or you don't have the second sequence showing. So click that button and that should actually bring it up here. Now the values of this particular sequence are much smaller in relation to this other one. Tell you what, let me make this just n plus 4. And then I'll bring the zoom back so we can actually make a bit of a comparison. All right, so you can actually see comparatively how the values of this sequence compare to this other one. So that's how that works. Okay, now there are two types of sequences that we explore more than others. These are called the arithmetic sequence and a geometric sequence. An arithmetic sequence, what happens is that the difference between every pair of consecutive terms is a constant. And what that means ultimately is that this is based off of linear changes. So you can describe an arithmetic sequence with a linear function. So because it's a linear function, it basically means you can express it as y equals mx plus b, where m is that constant rate of change. Of course, that's our slope. And b is like a y-intercept. But we're not actually going to intercept the y-axis in general here because, you know, n can't be equal to 0. That would be our input variable, and that's what we would need. But it works the same, okay? Just basically means a starting value. Now, let's take a look at this sequence, 3, 7, 11, 15, 19. So what you can observe is, you know, from the values, one value to the next, it's pretty clear what's happening here. We can get from one value to the next simply by adding 4. And you need to check multiple ones here just to make sure that that persists. And you can, of course, do this mentally, but, you know, that tells you that the slope of this, or the common difference, is 4. Okay, it's always 4. So that means the nth term of this sequence is going to be defined by 4 times n, your input variable. But that's not perfect, because the thing is, if you let n equal 1, that means the first term would be 4, but we don't have 4 here, we have 3. So you just need to make an adjustment, and that's kind of like what the y-intercept is. So when n is 1, you need the first term to be 3. So 4 times 1 minus 1 would give you 3, and then that checks out. And of course you can check a couple different values to make sure it works out, but it always should. So when n is 1, 4 minus 3 is, of course, 4 minus 1 is, of course, 3. And let's say this is n equals 1, 2, 3, 4, so a sub 4 would be 4 times 4 minus 1, which would be 16 minus 1, or 15. So it checks out. So let's find an explicit formula for the nth term of this arithmetic sequence. So we have 19, 10, 1, negative 8. What I notice here is going from the first to the second term, the value decreases by 9. The same is true going to the next, and so on. So that tells me that basically the slope of this is negative 9. But I didn't start at 9 times my variable. But it didn't start at negative 9. I started at 19. So I need to adjust this so that I start at 19 instead. So if you want, you can basically say, all right, so I need some value when added results in 19, and you could solve for it. And so we know that this happens when n is equal to 1, so negative 9 plus b equals 19 tells me then that this would have to be 28. All right, so a sub n would be negative 9n plus 28. And just check a few terms to make sure it works out. So when n is equal to, say, 3, a sub 3 should be negative 9 times 3 plus 28, which would be negative 27 plus 28, which is 1. And that's what we had for the third term. So that works out. The other type of sequence that we're interested in is the geometric sequence. And this happens whenever the ratio of every pair consecutive terms is constant. So this possesses an exponential relationship when changes occur. So for instance, when I have the sequence 2, negative 2/3, 2/9, negative 2/27, and 2/81. So that is a type of exponential sequence because if you'll notice, the numerator is always 2. So we can actually just leave the numerator as just 2. The denominator, however, changes, but it's not a linear change because if I think of it as a linear change, to go from, well, actually, the first term to the second would be plus 2. The second to the third would be plus 6, which is not the same. So it's not a constant linear change. But it's a multiplicative change because to go from 1 to 3, that's what it means. You could multiply by 3. 3 times 3 would give you 9. 9 times 3 would give you 27. So we have a multiplicative change here. And so that's exponential, which means the denominator is going to be 3 to the nth power. And that's not quite all, because there's also some terms are negative, some terms are positive. So that can occur with an alternating piece here. So for instance, if I multiplied the numerator or the whole fraction, doesn't really matter, by negative 1, that would make it always negative. But if I take negative 1 and raise it to the nth power, that actually alternates it. So negative 1 to the first power is negative. Negative 1 to the second power is negative 1 times negative 1, which is positive 1. Negative 1 to the third is back to negative 1. So it alternates. I just need to make sure I have the correct alternation. So for instance here, the problem is that when n is negative, or when on the first term, we have a positive value. So when n is 1, it's going to start out negative. So I needed to start with a positive value. So we'll just do negative 1 to the n plus 1. And one last thing, 3 to the n. We are correct in that this is a multiplicative change in the denominator, but kind of like with the numerator here, I can't start with negative 1 to the n because that would start with a negative number. 3 to the 0 would be 1, but not when n equals 1. So I need to make an adjustment there as well. So 3 to the n minus 1. And that gives me the nth term of this particular sequence. All right, let's try a couple other of those and see if we can come up with them. All right, so find an explicit formula for the nth term of the sequence, negative 1/2, 2/3, negative 3/4, and so on. All right, so we start with a negative value, and then we have a positive, and we have a negative, so we have an alternating sequence here. So that means I'm going to have negative 1 to the nth power or negative 1 to the n plus 1 power. I just need to make sure the negatives and positives line up. So this is a sub 1, it's negative, this would be negative. That works fine. All right, so that gets my alternating piece. All right, and then I have this fraction. The numerator is just increasing by 1 each time. All right, so if it's increasing by 1 each time, then that's a linear change. So we're starting with 1. So that's actually kind of nice. So that's just going to be n in the numerator. The denominator, 2, 3, 4, 5, 6, that's a linear change as well, but it's not starting at 1, it's starting at 2. So the denominator would be n plus 1. So there's an explicit formula for that particular sequence. So you might not have a sequence that's entirely linear or a sequence that's entirely geometric. It might be a mix, and you can still identify how those match up. Let's try this next one. So we have 3/4, 9/7, and so forth. Now, you really want to focus on the sequence of the numerator or the sequence of the denominator separately, because looking at the relationship of 3/4 to 9/7 is going to be kind of daunting. But if we just look at numerators, 3, 9, 27, 81, and so forth, these are powers of 3. That's pretty evident there. So powers of 3, but we need to make sure everything lines up. So when n is 1, we have 3. So 3 to the first is 3. 3 to the second is 9. So that's great. 3 to the n in the numerator. The denominator, to get from 4 to 7, we would add 3. To get from 7 to 10, we would also add 3. So add 3, and so forth. So the denominator here is linear. And it's starting, and so it has a common difference of 3, so it's going to include 3n. But we're starting at 4, so we just need to make sure the first value starts at 4. So if n is 1, 3 times 1 plus 1 would give me 4, and that makes the adjustment correct there. And so now I've come up with a function for this particular sequence.